Yes, last time I told you about the graph between lambda mc and concentration, square root of concentration of the electrolytic solution. Graphs are very, very important. Their explanation is very important. In case of strong electrolyte, lambda mc, molar conductivity at concentration C, increases gradually with the dilution. In case of weak electrolyte, molar conductivity increases sharply. I gave you reasons last time, which I need not repeat here. And I also told you that we can extrapolate the graph for strong electrolyte to infinite dilution, due to which lambda m infinity of strong electrolytes can be determined graphically. But the graph for weak electrolyte cannot be extrapolated to infinite dilution. Therefore, lambda m infinity of weak electrolytes cannot be determined from the graph. Now, I'm explaining next part before I dictate. So, as of now, we can determine lambda m infinity of strong electrolytes with the help of graph, but we cannot determine that value for weak electrolytes. Now, if we try experimental method to experimentally determine lambda m infinity of any electrolyte, this electrolyte should be completely ionized. It should be completely converted into ions. Then only we can determine lambda m infinity. Now, if it is a strong electrolyte, it is by definition completely ionized. But if it is a weak electrolyte, for complete ionization of weak electrolyte, solution has to be very, very dilute. And if the solution is very dilute, naturally number of ions per unit volume will be very low. And if number of ions per unit volume is very less, then the value of kappa will be very low. And if value of kappa is very low, naturally accurate determination of value of kappa is not possible. This is the reason lambda m infinity of weak electrolytes cannot be determined even experimentally, although for strong electrolytes, we can determine the value experimentally as well. Right on this part. To experimentally determine lambda m infinity, electrolyte should be completely ionized. Full stop. Since a strong electrolyte ionizes completely, its lambda m infinity can be determined experimentally. However, for complete ionization of, hold for a second, I'm coming. Yes, sorry. So you are writing, however, for complete ionization of a weak electrolyte, solution has to be very dilute, and the value of kappa, value of conductivity of such a dilute solution
So
will
the
be
solution has to be very dilute.
has to be very dilute, and the value of kappa, value of conductivity of such a dilute solution is too low to measure accurately. Too low to measure accurately. You remember in solutions also I told you that value of delta TB and delta TF are very small and therefore their accurate determination is not possible. We are applying the same thing here. Since the value of kappa will be very low, its accurate determination will not be possible. Right? Continue. That is why lambda m infinity of weak electrolytes cannot be determined experimentally, nor can the value for weak electrolytes be determined graphically, which I told you last time, graphically. However, its value can be determined by using Kohlraush law. Note it down. Kohlraush. By using Kohlraush law. So this is our next topic. Write down the heading. Complete name of the topic is, write down, Kohlraush law of independent migration of ions. I'll repeat, Kohlraush law of independent migration of ions. If you have to write again and again, you can please write K law. K law means Kohlraush law. See, in molar conductivity, we talk about, as per definition, molar conductivity is the conductivity of all the ions provided by 1 mole of the electrolyte. Now, if we know conductivity of one ion multiply by number of ions, that will be the total ionic conductivity of one type of ions. Similarly, second type of ions, number of ions multiplied by molar conductivity of that type of ions. It's something like this, that let us say there are 10 persons and everyone has the same mass. So what is the total mass of these 10 people? Mass of one person multiplied by 10. Almost the same type of topic. Pattern. It states that total molar conductivity of an electrolyte at infinite dilution is the sum of molar conductivities of all its ions at infinite dilution. Now copy the formula from board. Mathematically, lambda m infinity is equal to, this is capital lambda and this is small lambda. Lambda m infinity plus is a part of the symbol. This plus does not mean we are adding something. This plus specifies cation. right? So lambda m infinity plus multiplied by nu plus. Plus is again a part of the symbol. This is nu plus. This plus means we are adding. Lambda m infinity minus, here minus stands for anion, multiplied by nu minus. Till now we consider fifth equation. This will be sixth equation. Now label. This is total lambda m infinity, total molar conductivity at infinite dilution. Now lambda m infinity plus this is molar conductivity at infinite dilution of cations. Plus means cations. Lambda m infinity minus means molar conductivity at infinite dilution of anions. Nu plus number of cations. Number of cations per molecule. For example, if it is sodium sulfate, there will be 2 sodium ions. So nu plus ki value will be 2 and sulfate ion will be 1. Therefore, nu minus will be 1. So nu minus will be number of anions per molecule. Further write down. Lambda equivalent. This is the formula for lambda m. Now I'm telling lambda equivalent in infinity. Sorry. So molar conductivity at infinite dilution of cations or anions, that will be equal to its molar conductivity divided by n factor. So this is lambda m infinity divided by n factor, in this case nothing but charge. So if it is sodium ion, divide by 1. If it is magnesium ion, Mg is plus 2, divide by 2. If it is sulfate ion, again charge is 2, so divide by 2. Right? One more formula. Now this is for the electrolyte. Lambda equivalent infinity of electrolyte is equal to lambda m infinity of electrolyte divided by n factor. Divided by n factor. If you remember, I told you about n factor in normality. Just I'm trying verbally. Let us say molar conductivity of MgCl2, magnesium chloride, is 200. Then what is equivalent conductivity? 200 divided by n factor. And what is n factor for magnesium chloride? Anyone? What is n factor for magnesium chloride?
Sir, 2.
2. So 200 divided by 2, that is the n factor. Answer will be 100. Now I'm taking up 5 parameters and I'll tell you 2 relations between them. Right on next paragraph. Degree of dissociation within brackets alpha, comma lambda mc, comma lambda m infinity equilibrium constant.
Can you repeat, sir?
Okay. I said degree of dissociation alpha, lambda m infinity, lambda mc, degree of dissociation. For degree of dissociation,
Yes.
I done oblique uh, 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 dissociation constant, equilibrium constant, also called dissociation constant. Symbol is capital K. And fifth is concentration of solution. Concentration of solution are related to each other as given below. So these are 5 parameters. They'll be related to each other in 2 equations. I'll repeat. These are alpha K, that is degree of dissociation, lambda MC, lambda M infinity, and concentration of solution. For this, I'm giving you 2 equations, 2 relations. Alpha is equal to lambda MC divided by lambda M infinity. Equation number 7. And remember, value of alpha will always be less than 1 but more than 0, right? And second is K is equal to C alpha squared divided by 1 minus alpha. I'm giving you one more equation, but that will be with a caution. Alpha is equal to K by C under root. Remember, we cannot use equation 9 frequently. There is a restriction when to use this equation. Write a note. Write a note. Use equation 9. Use equation 9 only if it is mentioned, that the solution of electrolyte is very dilute. Now I'm sharing one numerical on WhatsApp. We'll solve it. Yes, check your WhatsApp message. Numerical is lambda m of 0.02 molar solution of weak acid H2A is 12 ohm inverse centimeter square mole inverse. Calculate its degree of dissociation and dissociation constant. That is, we have to calculate alpha and K. If lambda m infinity of H plus and A minus 2 ions are 130 and 40 ohm respectively. So first of all, I'm using Kohlraush law. Lambda m infinity will be 130 into 2, because the molecule H2A, one molecule will give 2 H plus ions, and the value for H plus ions is 130 multiplied by number of H plus ions, plus value for A minus 2 ion is 40, and there will be one A minus 2 ion produced. So multiplied 1 by 1, this would be 300 ohm inverse centimeter square mole inverse. Now, first value, we have to calculate alpha. Alpha will be lambda MC, that is given 12, divided by lambda m infinity 300, 0.04. This is one answer. Second, we have to calculate the value of dissociation constant. See, in the numerical, it is not mentioned that it's a very weak electrolyte. So we cannot use equation 9, we'll have to use equation 8. Now, K will be equal to C. C is 0.02 molar. Alpha is 0.04. So this is C into alpha square divided by 1 minus alpha. 1 minus 0.04. This will be the second answer, which is you'll find in the numerical, which I sent you on WhatsApp. So this is in text numerical 4. You'll find in the description box of video. Next topic. Applications of Kohlraush law. Applications of Kohlraush law. Number 1. See, if we know lambda m infinity value of ions, we can calculate lambda m infinity like this. So first application is to calculate lambda m infinity of strong and weak electrolytes from lambda m infinity values of its ions. Second point. For second point, let me explain. I told you these two equations, 7 and 8. Now, if I want to calculate the value of alpha, I need lambda m infinity. Lambda mc can be determined experimentally. So if I want to determine the value of alpha, naturally for the weak electrolyte, I want lambda m infinity. Lambda m infinity can only be determined by using Kohlraush law. So this is the application. Similarly, if I want to calculate the value of equilibrium constant, I want value of alpha. For value of alpha, again, I need lambda m infinity. And again, lambda m infinity can be determined by using Kohlraush law. So directly or indirectly, Kohlraush law has to be used. So write down second application to calculate degree of dissociation. Calculate degree of dissociation, that is alpha, by using equation 7 and to calculate equilibrium constant by using equation 8, for which lambda m infinity is determined by using Kohlraush law. Last application, very simple, but numericals are popular. To calculate lambda m infinity of a weak electrolyte by using lambda m infinity values of other strong electrolytes which can be determined experimentally. Means what? It means if we want to calculate lambda m infinity of a weak electrolyte, we can calculate by using lambda m infinity values of strong electrolytes, because lambda m infinity values of strong electrolytes can be determined experimentally. So we'll use those values for strong electrolytes and calculate lambda m infinity of weak electrolytes. How do we do that? For that, I've shared one numerical. Check your WhatsApp message. We'll calculate this one. Very simple numerical. Yes. Calculate lambda m infinity of barium chloride. If lambda m infinity of barium nitrate HCl and HNO3, lambda m infinity of these three strong electrolytes are given, we have to calculate lambda m infinity of barium chloride, which is a weak electrolyte. See, I want the value of one barium ion. For one barium ion, I'll use first value, that is for barium nitrate. And the value for barium nitrate is 120. But when I add one time the value of barium nitrate, no doubt I've taken one barium ion, but I've taken two nitrate ions which are extra. I'll have to subtract two nitrate ions. For subtracting two nitrate ions, I'll subtract the value of nitric acid two times. And nitric acid is 40. So minus 40 into 2. 40 into 2 means two nitrate ions have been subtracted, but at the same time, two hydrogen ions have also been subtracted. Now, I'll add two hydrogen ions by using 2 times HCl, and the value of HCl is 60. 60 into 2. So HCl ions, which were H plus ions, which were subtracted, they have been added again, but at the same time, two chloride ions have been added, which we wanted according to the formula, right? This plus 2 times this minus 2 times this. If you add these formulas, you'll get barium chloride. So when you add or subtract, you'll get the final answer. This will be 160 ohm inverse centimeter square mole inverse. This is the answer. Next topic. Now, few topics will be repetition of what you studied in 11th standard. It's there in syllabus of class 12 syllabus as well. So we can go with fast. At our next topic, direct and indirect redox reactions. Direct and indirect redox reactions. See, a redox reaction is nothing but transfer of electrons. If transfer of electrons between reactants is direct, direct means if the substance oxidizes and the substance reduced, they are touching each other, then electrons will be directly transferred between them. And that will be called a direct redox reaction. But if the substance oxidized and the substance reduced, they are not touching each other, then electrons have to be passed from one substance to the other through some other medium. That will be called an indirect redox reaction. And we'll be dealing mainly with indirect redox reactions in remaining chapter. So write down a direct redox reaction. A direct redox reaction is the one in which substance oxidized and the substance reduced are in contact with each other and there is direct transfer of electrons between them. For example, a zinc rod dipped in copper sulfate solution. In these reactions, energy is released in the form of heat. Energy is released in the form of heat. So if you touch the test tube or the beaker, it will become hot. Next paragraph. An indirect redox reaction is the one in which electrons are indirectly transferred between reactants. In these reactions, energy is released in the form of electricity. Is released in the form of electricity. So I'm not giving example because remaining chapter will be based on indirect redox reactions. Right on next topic. Electrochemical cell. Electrochemical cell oblique galvanic cell oblique voltaic cell. Electrochemical cell oblique galvanic cell oblique voltaic cell. As I said, it's a repetition, so please, we can be a little fast. It is a device. It is a device in which an indirect redox reaction takes place and energy released during the reaction is directly converted into electricity. Now there'll be sub parts of this electrochemical cell. Right on the subheading, construction of electrochemical cell. Please draw a rough diagram. This is zinc sulfate solution. This is copper sulfate solution. This is copper rod. This is zinc rod. Diagram is not complete. I'll dictate for this much. Whatever I've drawn, I'll dictate for that. Then I'll add something and add and dictate in part also. Consider the Daniel cell. This is called Daniel cell. Daniel. Consider the Daniel cell. It consists of zinc rod dipped in zinc sulfate solution and copper rod in copper sulfate solution, which are called redox couples. they are represented as zinc ions oblique zinc and copper ions oblique copper. They're represented as zinc ions oblique zinc and copper ions oblique copper, respectively. Two metal rods are connected through wires and voltmeter, but there is no deflection in voltmeter. No deflection in voltmeter. When solutions are connected through a salt bridge, now add this in the diagram. This is salt bridge. Right? Hope you have added in the diagram. So I'll repeat, when solutions are connected through a salt bridge, voltmeter shows deflection, that is current flows. Now next subtopic, write down preparation of salt bridge. How do we prepare this salt bridge? Preparation is very simple, but we have to take one or two very simple precautions. Write down. I'll not dictate complete sentences, short. In short, we'll write that in a beaker, take distilled water plus agar agar gel powder, AGAR, AGAR, agar agar gel powder plus salt of a strong acid and a strong base whose cations, this is a very important precaution which I'm going to dictate, whose cations and anions have similar mobility. Similar mobility. For example, KCl, potassium chloride, KNO3, potassium nitrate, NaNO3, sodium nitrate, ammonium nitrate, NH4 and NH4NO3, etc. So these are the electrolytes which can be used. Their ions, that is cations and anions, they have similar mobility. So heat and prepare. So we have taken all these things in a beaker. Now heat and prepare a saturated solution. Fill the hot solution in a U-shaped tube and cool so that the jelly sets into a semi-solid mass. The jelly which you eat, same type, sets into a semi-solid mass through which ions can freely move. So jelly will not move, but ions of the electrolyte, they can freely move through this jelly. So one precaution is that the electrolyte should be one whose cations and anions have similar mobility. There's one more precaution. Write down in the second paragraph. However, if KCl is used, then no, change the language. However, KCl should not be used in making KCl should not be used in making the salt bridge if the cell contains Ag plus, that is silver ions. So on in any one of these two half cells, silver salt should not be present. Hg plus 2 ions, mercurous ions. Pb plus 2, lead ions, or Pl plus, thallium ions. I'll repeat. So KCl should not be used if any one of these ions is present in the electrolyte, as present as electrolyte. I'll have to repeat the sentence. KCl should not be used in making salt bridge if so and so ions are present in the cell, because these ions combine with Cl minus ions, chloride ions, and lead to the formation of precipitates of AgCl, Hg2Cl2, PbCl2, and PlCl respectively at the mouth of tube of salt bridge, so that the flow of ions through salt bridge will stop and salt bridge will stop working. Now I'll explain. This was the last sentence for today. I'll explain what is the meaning. See, you have written that we should not use potassium chloride in making the salt bridge. Why? When should we not use potassium chloride in making salt bridge? When silver ion or mercurous ions or lead ions or thallium ions, they are present in one of the electrolytic solutions. What is the problem with these cations? All these cations will combine with chloride ions of KCl and lead to the formation of these precipitates. And these precipitates will block the mouth of U-shaped salt bridge. And once the mouth of the salt bridge is blocked, flow of ions will stop and this salt bridge will stop working. So this is one precaution. And the second precaution, which I told you earlier, was that mobility of cations and anions of electrolyte used should be similar.